Welcome to lecture 3.2 of Bio 6612. In today's lecture, we're going to cover the likelihood function for logistic regression and the MLE for coefficients in logistic regression. Let's say we have n random variables that all follow a Bernoulli distribution. So we already know that the probability distribution for a Bernoulli random variable looks like this. And we have a particular model for pi I, or the probability that yi equals 1, given the set of covariates xi. And that is this logit model that we talked about in the last lecture, where logit of pi I is equal to xi beta. This is just in matrix notation here, where for beta 0 plus beta 1 x1i plus beta 2 x2i all the way up until beta px pi. And so how do we compare? So how do we combine the PDF that we have and the model that we have written down here to get the likelihood for our logistic regression model? And just for simplicity's sake, I'm going to write this out where xi beta just equals beta 0 plus beta 1 x1. So we only have the intercept and one covariate in this model. Well, you would go about writing this out the same way you would for a regular likelihood, where you have the product from I equals 1 to n of all of the different PDFs which we can plug in the PDF here. But now we also have a model for pi I in terms of our x's and our betas. So we can plug that in as well. I'm just substituting this pi here for this expression the inverse of this, which is just pi I equals e to the xi beta. So that gives you e to the beta 0 plus beta 1 x 1i all to the yi times 1 minus e to the beta 0 plus beta 1 x 1i to the 1 minus yi. Okay, and that is your likelihood function. And notice before we had pi I as the parameter of interest. Now we no longer have that. Instead, what we have are these betas, and those are the things that we want to estimate. So the likelihood is now in terms of beta 0 and beta 1, given your observed yi and xi. So that brings us to, that brings us to the same likelihood that I have written down here. And this is just, here we only have beta equals beta 1 and beta 0. But this would generalize to p betas if you have p covariates in your model. And then if you take the log of that, it gives you the log likelihood, which is given here. And before we were modeling this as logistic regression, when we were just calculating the likelihood of the Bernoulli distribution, we were able to bring this log out of the summation. But now, since we have the xi's, we can no longer do that. So what are the parameters that we want to estimate now in this model? Well, if we observe the data, we collect, let's say, covariates and an outcome of interest, then we already know our y and our x values. And what we're looking for are those coefficients. And how do we get those coefficient values? Well, we can get them using the maximum likelihood estimators that we learned about before. And in principle, we solve this exactly for the MLEs of beta 0 and beta 1 in exactly the same way that we have before to obtain estimates for your regression coefficients. And as a refresher, we did that by getting the score function. Let's say we want to get the estimate for beta 0, and that's the derivative of the log likelihood with respect to beta 0. And then we set that equal to 0 and solve for beta 0. And so I have that written out here in this next slide. So if we have p covariates, say x1 to x2 all the way up to xp, then we're going to have p plus 1 score functions that we need to solve for, where the plus 1 comes from the beta 0. So if you have x equals 2, or sorry, p equals 2, so then you have covariates x1 and x2, and you have coefficients beta 0, beta 1, and beta 2 that you want to solve for. In the example here, we only had p equals 1. So we only need to estimate the intercept and the beta 1 coefficient. And there's a score function for each one. And so the way that you would get each of these equations, this is a partial derivative, meaning that the partial derivative of the log likelihood with respect to beta 0 is taking the derivative of that log likelihood function we saw in the previous slide, assuming that everything except for beta 0 is a constant. And similarly, to calculate the partial derivative of beta 1 with respect to the log likelihood, you would assume everything except for beta 1 is constant and take the derivative with respect to beta 1. And you can actually take those derivatives yourself. They're quite messy, but you can do it. There's a lot of use of the chain rule. However, the solution at the score equal to 0 cannot be obtained by hand or analytically. So you can get that derivative, but if you said equal to 0, you can't actually solve for beta 0 and beta 1. You just get an expression for what the score is in terms of beta 0 and beta 1. Similarly, we could calculate the information for the coefficients in logistic regression the same way that we have in previous lectures. And before this, we've only seen an example where the information is a single number. And that's what you'll get when you only have one parameter that you're trying to estimate. However, when you have multiple parameters that you're trying to estimate, the information is actually a matrix and not a scalar value. And the size of that matrix, the number of columns and rows, it's going to be a square matrix with equal columns and rows, equal to p plus 1 columns and p plus 1 rows, where again, p is a number of covariates in your model. And that is a matrix of the partial second derivatives of I with respect to those parameters b, beta. So again, if I have only p equals 1, and my two parameters then are beta 0 and beta 1, so I'm going to have a 2 by 2 matrix. with 4 elements. And then each element is given here. So the first element is the second derivative of the log likelihood with respect to beta 0. That's going to be the inverse of the variance for beta 0. The last element is the second derivative of the log likelihood with respect to beta 1, which is the inverse variance of beta 1. And then you have these cross-diagonal terms, which are actually equivalent to each other. You would say that this is equal to this. And that's going to be the partial derivative of the log likelihood with respect to beta 1 and beta 2. And this is where you get the covariance of beta 1 and beta 0. Again, I'm not going to go through the calculations of actually taking each of these derivatives, but in principle, you use this information matrix for the beta coefficients the same way that you would for any other maximum likelihood estimator. So how do I actually solve for these values? As I mentioned, you can't actually solve these equations analytically by hand, at least in the logistic regression case. For other exponential family regressions, you can. So in order to obtain MLE estimates, you need to get them numerically. And there are numerical algorithms that are, many of them actually out there, that allow you to do this. And what numerical methods for obtaining the MLE do is they search through all the different possible values of beta 0 and beta 1 to obtain values that give the highest possible value of the log likelihood. And then why did we even bother with that information matrix? Well, the numerical methods to maximize the likelihood only give you a point estimate, a single value that is the maximum likelihood estimate for beta 0 and beta 1, but it doesn't give you like p-values or confidence intervals. It doesn't give you inference. So in order to actually do inference, you also need a numerical estimate of the information matrix. And one thing that's kind of nice to note is that the information is often called the gradient in numerical optimization settings. So statisticians might call it the information, engineers might call it the gradient. So how do we actually go about finding that MLE numerically when we can't solve for beta analytically? You use a numerical algorithm. And I'm not going to go through the actual steps of the algorithms that you can use. There's a ton out there, a ton of algorithms that you can use to maximize any sort of function that you're interested in. The maximum likelihood is just one example of a function that you might want to find the minimum or maximum of. But I am going to show you a couple examples of numerical ways of finding that MLE. And the example comes from this 2x2 table where the outcome is lung cancer, yes or no, and the covariate of interest is exposure to secondhand smoke, or called passive smoking in this data set, where the variable passive can take on a 0 or 1, 1 indicating exposure to passive smoking and 0 indicating no exposure. And here Y are cancer cases, and then N are the just total number of observations for each of those groups. So one example of a numerical method that you can use to calculate the MLE is called Fischer scoring. And actually, both SAS and R programs fit logistic regression models using Fischer scoring. And this is a numerical optimization technique for MLEs that's specific to generalized linear models that uses both the score function and the expected Fischer information that I showed you a few slides earlier. So in R, we fit the logistic regression and other GLMs using the GLM function. And so GLM's default calculation for the MLE of your coefficients is Fischer scoring. So this will give you the Fischer scoring estimate. This is one way of running an MLE. This is one way of running a logistic regression in R, and I'm going to go through more modeling details at a later lecture, but basically we're modeling, here I'm modeling the ones and then the zeros against the outcome, which in this case is exposure to secondhand smoke. The family is binomial because we have binomial data, and we get a value here, which is an estimate for the and so what logistic regression is actually doing here, this is running the logistic regression model. It's getting an estimate for that information matrix. It's getting the MLE estimate using Fischer scoring for those coefficient values, and it's using the estimated information matrix to give you p-values and confidence intervals for your coefficients. And as part of that, it also calculates your log likelihood based on the values of the coefficients at the MLEs, beta 0 hat and beta 1 hat. And here's your actual value of the log likelihood at those MLE estimate values. It's negative 6.649, roughly. So that was just one example of how you can use numerical optimization to get MLE estimates, and one that's specifically used in GLM type models. But there are many more general numerical optimization techniques that exist. And the goal for these methods is to optimize, meaning minimize or maximize, some function that can't be solved by hand. And these are applicable to much more general settings than just GLMs. In fact, they're used all the time in machine learning to estimate whatever parameters you're trying to estimate. In fact, these are all used all the time in machine learning, in engineering, in image processing, and there are tons of other examples where numerical optimization comes into play. And so the first thing that you need to do in order to go about doing this in a more general way is define the function that you're interested in optimizing. And so in our case, we are interested in optimizing the log likelihood function for logistic regression. And this is a function that depends on the beta values, the y values, the x values, and then n, which is the total number of trials. And so I've defined this function as such. We have eta, which is your x values times your beta coefficients. That's your x beta, your linear predictor. We've defined pi. That's your probability that yi equals 1 given your x covariates x. That's something else that goes into the log likelihood. And then the actual log likelihood can be calculated by summing up for all the trials and the y values. Then the log likelihood itself is calculated by using the pi and the x betas to get the density across all of the different independent y's. So we defined the function with the code chunk here, and then I can actually call that function and plug in different values to get a particular log likelihood number. So here in this case, I'm plugging in the y values from our data, the n values from our data, and the x values from our data. And then I'm plugging in the beta values that we obtained from that logistic regression and the GLM function from before. And you can see it gives you for the number for the log likelihood, which is negative 6.649, which is the same number that was spit out by our GLM function in the previous step. Okay, so how do we use this to actually calculate? So how do we use this in a numerical optimization algorithm to actually give us an estimate of our betas, however? Well, if you want to use this in a numerical optimization algorithm, you have a definition for your log likelihood function, but without having run that GLM function before, we wouldn't know what betas we need in order to maximize this function value. So you usually have to feed it some sort of guess, some starting guess to get the algorithm started. And it's common to give what's called an uninformative starting guess. In this case, I'm using a starting guess of 0, 0, where both betas are equal to 0 in the model. And you can see just checking, what would you expect to happen to the log likelihood if you plug in betas that are different from the maximum likelihood estimator? Well, you would expect the log likelihood to have a smaller value because the log likelihood is supposed to be maximized, have its highest value at the MLE estimates for beta 1 and beta 0. So good to double check that. Here I've plugged in estimates of 0 and 0.5 for beta 0 and beta 1, and that gives us a log likelihood value of negative 11.8, which is less than negative 6.649, which is the value we get when we plug in the MLEs. So that's good. That sort of checks our understanding of what it means to be the log likelihood. So good, that sort of checks our understanding of the problem. Okay, so in the second code chunk down here is where I actually call the numerical optimization algorithm that allows you to calculate an MLE value for beta. And you can do this using this function optim, which just comes as part of base R. And there's several arguments for this function that you have to plug in. The first are starting values for your coefficients. This is start beta. Here, this is a vector of size 2 because I have beta 0 and beta 1. But if I had a problem where I had 3 coefficients, say beta 0, beta 1, and beta 2, then this would be a vector of size 3 because I would need to have 3 initial values. The second argument is the function that you want to optimize, which in our case is the log likelihood for logistic regression. This argument here, Hessian equals true. You can have Hessian equals true or Hessian equals false. when you have Hessian equals true, that calculates the numerical gradient or an estimate of the information matrix. So you can use that to obtain inference about your MLEs of beta. Then here, these are all plugging in arguments to the function that we defined above. So these are plugging into the log likelihood that we defined earlier. Y, N, and X mat are all arguments for that. Method equals BFGS is just the optimization method that I'm using in this case, which I'm not going to talk about, but there are a ton of different methods out there that do numerical optimization. And then finally, this control parameter says the function scale is -1. All of this is doing is that, so the default for optim is to actually minimize this function, and we want to maximize it. So this is just telling this optim function that, hey, we actually don't want to find the minimum of this log likelihood, we want to find the maximum of this log likelihood. So we go ahead and run this code, and it will calculate an estimate of the maximum of the log likelihood for these parameters beta 0 and beta 1. And let's check the values that we get. Let's compare our estimates that come from GLM and Optim. Okay, so the first row here gives you estimates from GLM. And this one gives you estimates from Optim. And look, they're pretty similar, which is great. Both of them give similar estimates for your maximum likelihood. And then similarly, we can calculate our covariance matrix, the covariance of beta 0 and beta 1. And so in a few slides earlier, we looked at the information matrix of beta, which was a 2x2 matrix. The covariance is also going to be a 2x2 matrix that is equal to the inverse of that 2x2 information matrix. And that's given here. They have two estimates. And this first block is from GLM, and that second block is from Optim, calculated using that Hessian argument. And again, both of these are quite similar as well. And these are used to actually get your inference, which we'll talk about in a later lecture.